Hey, so I'm Douglas Keong, and I'm going to walk you through a unplugged activity that teaches kids or anybody really about the binary number system and how you can represent a decimal number with a lot of ones and zeros. And so I usually start with a story or hypothetical situation. So let's imagine that we're in a land where you have a ones coin, you have a twos coin, a four coin, and an eight coin. And so I run a store and you can buy stuff in my store for different amounts of money, and nothing in my store is for free. So I might say, okay, what's the cheapest thing that you can buy in my store? And the cheapest thing would be something that costs 1 cent. So 1 cent or 1 unit. Um, uh, if you're doing this in another country, I would often use just, widgets or zarblots or just some made up thing. But, US, I usually just say cents. So 1 cent. What's the most expensive thing that you can buy in the store? Sometimes kids will say eight. It's not 8 cents because you could say, well, what if it was 9 cents? What would you use? You'd use an eight and a one. So you could buy something that was 9 cents. Oh, okay, I get it. Oh, all right. So then the most expensive thing you can buy is eight plus four plus two plus one, which is 15. So 15 cents is the most expensive thing that you can buy. If something was 16 cents, you can't buy it. You don't have enough money. Most people get that idea. So then the question is, all right, so let's imagine that in my store, I don't give any change. So you have to have exact change only. So what are all the items in my store for which you can't buy them because you don't have the right amount of change? Um, and then I'll usually give an example. So I'll say, like 13, for example. Like you can't buy anything that's 13 cents because you don't have exact change for 13. At which point everybody starts going, oh, wait a second. No, you can do 13. You can do 8, 4, and 1. And then I'll say, oh, okay, that's a bad example then. What I meant to say was something like 11 cents. You can't buy anything that's 11 cents. And then someone else will go, oh, no, wait, you can because it's 8 and 2 and 1. And that's how you kind of get across. And then people start going, oh, wait a second, let me see if we can figure this out. And so we think about it, and you can buy something that's 1 cent, you can buy something that's 2 cents, you can buy something that's 3 cents, you can buy something that's 4 cents, you can buy something, and so on and so forth. And so eventually, so I'll let them think about this for a few minutes, and then somebody will start raising a hand, going, oh, wait a second, you can buy everything. And I wait until we can get agreement in the group. So I'll say, does everybody agree that the least expensive thing you can buy is 1 cent? The most expensive thing you can buy is 15 cents. And you can buy every amount in between 1 and 15 inclusive. And once I get everybody to agree on that, then I'll say, okay, then the second thing I'd like to see if we have agreement on is that there is one and only one way to make each of those values. And once we get everybody's agreement that you can make every number between 1 and 15, and that there is only one way to make every number from 1 to 15, then I might say, okay, well, what by extension would what would be the next coin? And the next coin, of course, would be a 16 coin. And I usually do these with counters. I'll have like paper counters and have kids like cut them out, and so they can use those counters. Um, and sometimes I've even done things where I hand everybody an index card and say, cut up the index card into pieces. They can be square coins, and then you can give yourself another coin if you like. And just to start keeping these simple, I'll have people line them up in order like this. So we'll go 16, 8, 4, 2, and 1. And now, of course, the new maximum is 31, right? The most expensive thing you can buy is 16 plus 8 plus 4 plus 2 plus 1, 31. Cheapest thing you can buy is 1 cent. So we can go everywhere from 31 down to 1. And just to kind of make things simple, I have them on their piece of paper draw a line and then some columns just to kind of keep them straight. And so essentially we have something like a cash register. And so now I'll say, okay, the coins that you're not using will leave above the line. The coins you are using, you'll move below the line. So for instance, something that's 2 cents, I'd move the two down. If it's 3 cents, I'd move the one down. If it's 4 cents, I'd put these back and bring the one down. And so I'll have kids practice making different values. So I'll say, hey, let's make 27. How would you do 27? Well, you'd use 16, and then you'd use the 8. That's 24. If you add the 4, that's too much, right? That would be 28. So we would add the 2, and that gets us to 26, and then I add the 1, and that gets us to 27. So that's pretty cool. So this keeps track of what you're using and what you're not using. And what we can do is we can label these and we can say, okay, let's just say that if we're not using it, it's above the line. Another way of saying that we're not using it is just saying no. So in other words, no, 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 yes. You can also shortcut no. You know, in computer science, no is also 0. So this could be 0, 0, 0, 0, 1. And you'll end up with something like that. We could have a bunch of zeros here. 0, 0, 0, 0, 1. But now if we use our example and we said, okay, let's make 27, 27 looks like this. And so essentially at this point, we're not using the zeros. We'll throw them up here. Well, I think we're going to use this one because that's a 0. And we've got ones. So 11011, that is essentially binary code for 27. So 11011 is the same thing as 27 in binary. And often what we'll do in binary is we will actually put a little subscript here, and we will you'll see it down below. You'll see it down like this. So it'll be 110112. Now there are essentially, each one of these is a bit. A bit is two values, a 0 or a 1, a yes or no. So this is 1, 2, 3, 4, 5 bits of information. If you carry this out to 3 more places, you'll have 32, 64, and 128. And so 128, 64, 32, 16, 8, 4, 2, and 1, that's 8 bits. Another word for 8 bits is a byte. So you'd have 8 bits is 1 byte. So in 1 byte of information, you can store 8 bits. The maximum number that you can get in 8 bits is 255. So 255 essentially in binary is 111111, because you're using, was that 7? I'm going to say I'd said 8 ones. Anyway, 8 ones in a row. That's that's a binary code for 8 bits, or in other words, 1 byte. 8 bits, by the way, if you can store any number between 1 and say 255, well, you know, 0 also counts too. I mean, you could say 0. But what we can do is often you'll see the color picker. The color picker is actually pretty cool because color on the screen is always a mixture of red, green, and blue light. And unlike paint, if you mix 255, 255, 255, so full red, full green, full blue, you end up with white. And what we use in computer science is we'll use 255, in other words, 8 bits of information to encode how much red, how much green, how much blue. Now, the cool thing is, you know, we could create, let me just go ahead and create a new slide. And let's go ahead and change the background to be whatever this color is. And so what we can do is we can take, for instance, all the red and all the blue down and give it full green. And so the way that we would represent this as an RGB color is 0, 1111, 1111, and then 0, 8 zeros, 8 ones, and 8 zeros. And you'll end up essentially with a single number, or well, 3 sets of numbers that indicate a certain color. What happens if we mix in full green and full blue? We get like a teal color. You can play around with this and you can kind of come up with different kinds of color values. And on the web, well, this is kind of interesting. Full red and full green gives you kind of a yellow color. So red plus green, full red, full green gives you a yellow. You can give, you know, different colors like this. And on the web, the way that we represent these is we represent these in another numbering system called hexadecimal, which is beyond the scope of this activity, but it's basically another way of representing numbers. So 128 in binary is going to be, I think it's like 0, 0. I think there's a 1 in there, and then there'll be a bunch of zeros, right? In hexadecimal, it'll be 8, 0. But anyway, we're talking about binary. So 128, let's go in here and figure this out. So for 128, it'll be 16, 32, 64. Oh, so it'll be one and then seven zeros will be your 128. Um, the other thing that's kind of cool, now, now that we're kind of getting used to doing binary, is you can pull up the good old Mac calculator and you can change it. If you hit Command 3, you can actually change it to a binary calculator. So notice that if I put 128 in here, you'll notice that these registers, this is our first byte of information. So 1111, 1111, 1 in the 128th place, and then zeros for the rest of them, that gives you 128. And then the other thing you can do is if you click on these, I think we had said our 27 was, I think the one bit was turned on and this place was turned on, and then I think we had maybe a few more. Yeah. So 11011 is essentially 27. So even on the Mac calculator, if you put it in programmer mode, you can just go to the calculator screen and I think it's actually in the view screen and you can change it to programmer. But you can actually turn the bits on and off up here and play around with, okay, 2 would be there and then that's 3 and then 4 means this one's turned on and this one's turned off and then that would be 5 and then 6. So you can play around with binary that way as well. But the idea for students in this course is they need to be able to freely convert between base 10 and base 2, which is binary. And I think they probably also need to know base 16, but that's a different lesson to teach about hexadecimal. But for the purposes of this, to be able to go back and forth between binary and base 10 is good. I like this because it's a very concrete example using money that most people are familiar with. And then when you bring in this idea of colors, often kids who are budding web designers, or they may even have worked with colors on the web, all the colors on the web they're all displayed in terms of this hexadecimal code. So understanding about different numbering systems and that you can use different numbering systems to represent the same number. That's kind of the big takeaway here. Um, so I had one last thing I was going to say. I can't remember what it was, but it's the whole point of this activity is it's a really neat way to introduce this concept in a way that's familiar to a lot of people. What does happen sometimes is some people who are math teachers especially, they'll want to see this in terms of place values. And so this is essentially like 2 to the 0. If this was a superscript, so this one could be, this will be smaller, I guess. I'll try to make that. No. Anyway, this is 2 to the 0. I'll just do that. This is 2 to the 0, which is 1. 2 to the, oops, come on. 2 to the 1 is 2. 2 to the 2 is 4. So these are really places of 2, right? These are powers of 2. So 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5th, 2 to the 6th, 2 to the 7th power, 2 to the 8th, 2 to the 7th power essentially give you 128. And then 2 to the 8th will give you sort of into the next byte of information. And so you can view these as powers of 2 in the same way that when you work with base 10, these are powers of 10, right? This would be 10 to the 0 is 1, 10 to the 1 is 10, 10 to the 2 is 100. So we talk about when we learn math, hundredths place, the tenths place, the ones place, that kind of thing. But for me as a student, place values of powers of 10, it never totally made sense to me. So that's why this system works really nicely for me. You just think about it in terms of numbers of coins, essentially, and buying stuff, because a lot of us are familiar with, most kids, I think, are familiar with buying things with coins. Who knows how long that will last, but at least for now, this works. So hopefully this makes sense. Hopefully this is something that you can repeat for teachers that you're training or for students that you're teaching. And there's all kinds of neat connections and ways that you can modify this activity. And I'm hoping that we can share that with each other to come up with other ways to extend this activity. But by all means, go ahead, modify it, change it, do whatever you can with it to kind of get the point across. The idea is to get the point across of binary numbers and going over to decimal numbers. So thanks a lot and have fun converting.